Okay, good morning, everybody. Welcome. I'm Sandro Fiore, and the head of the Advanced Scientific Computing Division at the Euromed Center on Climate Change Foundation. And I'm very pleased today to act as moderator for this webinar. So this webinar is given by Valentine Anantaraji, who is computational climate scientist at Oak Ridge National Lab in Tennessee. So the talk relates to climate data management aspects in the context of the Energy Exascale System Modeling Project E3SM. So before getting to the presentation from Val, as hosting institution, let me just briefly spend a few words to introduce CMCC Foundation. So basically, CMCC is a non-profit research organization established in 2005. In 2015, the center became a foundation. CMCC is a scientific research center on climate change and its interactions with the environment, the society, the world of business, and policymakers. So our work aims to stimulate sustainable growth, protect the environment, and develop strategies for the adaptation and mitigation of climate change. Next slide, please. So the center is organized in the form of a network distributed throughout the country with locations in Lecce, Bologna, Capua, Milan, Sassari, Venice, and Viterbo, which involves and connects public and private entities working together on multidisciplinary studies concerning issues of interest to the climate scientists. Next slide. So CMCC scientific activities are distributed among 8 research divisions, which share different knowledge and skills in the field of climate science. Next slide. So these are just key topics I work on and we study at CMCC. So this goes through economics, policy, society, simulations, predictions, computing, modeling, impacts, and so on. Next slide. Okay, so of course this is a webinar which is part of this CMCC series of webinar, but of course we do a lot of outreach activities, for instance, scientific publication, international journals, educational programs, events, and communication activities for the public at large. So next slide, please. I just want to anticipate that there will be a question and time after Val's presentation, and so I kindly ask you to be very active and to post some questions. I will just pick up some of them during the question time and forward this to Valentine. So coming back to our webinar today, as I said, this will be done by Valentine Nataraji, who is computational climate scientist with the Scientific Computing Group in the National Center for Computational Sciences and CCS. Prior to joining Oak Ridge National Lab, he was an associate research professor at the Geosystems Research Institute, GRI, as well as adjunct faculty with the Department of Electrical and Computer Engineering at Mississippi State University. So he holds a PhD in computational engineering, a Master of Science in Meteorology, and Bachelor of Science in Physics. So Valentine was a NASA Enterprise for Innovative Geospatial Solutions graduate fellow for 2 years during his graduate studies. Prior to his tenure at GRI, he started his scientific career as an associate scientist at the former Institute for Naval Oceanography managed by UCAR. And Valentine has a broad professional experience in the areas of scientific data management, machine learning, applications of climate data, software engineering and applications development for operational implementations, decision support frameworks, integration of remote sensing data numerical models, satellite precipitation estimation, and regional climate modeling. His recent research interests include land surface hydrology, land-atmosphere interactions, and characterization of uncertainties in global climate models, particularly short-wave radiation. And Valentine's focus is on advancing the leadership scale climate modeling activities at NCCS in Oak Ridge. So after Valentine's talk, I will open the discussion with some first comments and on the topic, and then I'll open the floor to all the registrants and we'll pick up some of the questions that we'll receive during the webinar. In this regard, when you post a question to the webinar, I kindly ask all the participants to specify name, country, and affiliation. And of course, invite all the participants to be very interactive during the question time. I just want to remind you that the webinar is being recorded and the link to the video will be shared with all the registrants, as well as uploaded on the CMCC website. So, moving back to this talk, Valentine will present the webinar Managing Data in Large-Scale Climate Modeling Projects. Valentine will touch several interesting topics that span from data management, modeling aspects of workflow, looking forward to the exascale scenarios. So from a data and computational perspective, this will be a very inspiring talk. So that's it for the introduction. Now I can look forward to our speaker, and I will turn off my camera and microphone. So Valentine, the floor is yours.
Okay, thank you, Sandro, for the introduction, and thank you also, Sandro, Professor Giovanni, Alessandra, and many others who have helped me prepare for this webinar and have it set up, and thank you for the invitation and the opportunity to share this webinar with you. And I want to give you a little bit of an introduction about, provide an outline on what I'm going to be talking about. So I'm affiliated with the Oak Ridge National Laboratory, and I have been part of this United States Department of Energy climate modeling, or rather the Earth System Modeling Project called E3SM. So I will tell a little bit about the project, what the project is about, and I will also discuss the importance of being able to manage the scientific workflow of such a large-scale project, and also the data management activities. And I will summarize my talk and just allow some time for the questions. So the Energy Exascale Earth System Modeling Project is sponsored by the United States Department of Energy. So it's a multi-laboratory project, and essentially it's to develop and deploy a new Earth system model. I call it new, but it was branched off the Community Earth System model. And it's not only the model development, also perform a set of simulation experiments, and then be able to enable the Department of Energy to be able to make the kind of decisions that need to be made that are relevant to the U.S. Department of Energy mission. And also, there's one unique aspect of what this modeling project is about, is that the Department of Energy also operates some of the largest computers. During the past decade or so, or longer, the Department of Energy has always had a handful of computers in the top 10 of the top 500 list in the high-performance computing resources. So there are some challenges in developing and optimizing applications for this leadership class computers, as we call it. So that's another one of the major motivations for developing a new Earth system model that is optimized to run on this leadership class systems. Currently, just a few weeks ago, in June, there was an announcement about our new leadership class computing system called Summit, which is currently ranked as the #1 system in the world. And these new generation of computer systems have heterogeneous architectures, and they pose a lot of challenges in being able to develop software and make them run effectively on those really leading edge hardware. So the project elements of the E3SM project, and the model also shares the name. It's referred to as the E3SM model, and the project also has the name. So it is to perform a series of prediction and simulation experiments. And the modeling system consists of, actually, it is a system of models, as most Earth system models are now. It is just not one monolithic model, but rather it's an aggregation of a number of models that feedback on each other and communicate with one another. And it's also, as I mentioned a little earlier, that the E3SM model is designed and developed to take advantage of the leading edge computational facilities from the Department of Energy. And the aspect that I'm going to be talking about is what is referred to as an infrastructure or a framework to support the entire modeling activity on how to design the experiments and develop the hypothesis, and how do we perform the experiments to test the hypotheses, which will involve a number of simulations across many computer platforms, and be able to seamlessly analyze the results so that one can derive the results, synthesize them, or make decisions based on it. The science questions the E3SM project deals with basically three broad topic areas. One is related to the water cycle. So to understand with climate change, the drivers and the shifts of water availability, which is critical not only for energy, but for a lot of other sectors of the economy and society. And then by geochemistry to study how the carbon allocation among the different components of the Earth system, namely the atmosphere, land, and ocean, and what are the feedbacks that are related to it. Another factor which is of great concern to society is the impact of sea level rise. And particularly in this E3SM project, we would try to understand through our experiments, modeling experiments, the contribution of the Antarctic ice sheet to the sea level rise with the projected climate change scenarios. The roadmap for E3SM calls for a set of major simulations, which the project started about 4 years ago, and what we call V0 through V5, version 5, V stands for 5. V0 is basically the baseline that we started with as we forked off the CESM model. And currently, the version 1 of the model has been released in end of April. And not only the model was released, at that time, we also completed the major set of deck experiments, and that is also, those data have also been released, a majority of it. And we have already started development for version 2 of the model. And during phase 2 of the project, there will be version 2 will be developed and completed. And also concurrently, we'll start development for the version 3. So that's the simulations, and this roadmap shows how those different versions of the model map to the different model development activities. And also interestingly, you know, how do they match up with the roadmap for the leadership computing architectures? The Summit, as you saw, is the latest, and the other one will be the next generation, will be the Exascale machines, which will be released, which will be deployed at the Argonne National Laboratory in the 2021 timeframe. And also concurrently, there will be another Exascale system, which will follow that shortly, called Frontier, which will be deployed, currently scheduled to be deployed here at the Oak Ridge National Laboratory. So the current generation is 100 plus petaflops, is some aspects of the version 1 as well as mostly version 2 of the E3SM model will take advantage of the Summit architecture. And then version 3 and beyond will take advantage of the Exascale machines that are scheduled in the early 20s. So I'm going to now go ahead to the main topic of, with that background in E3SM, I would like to talk to the data management and the scientific workflow challenges that we face. So the entire E3SM project is centered around being able to answer critical science questions. So based on the science questions, we design the experiments and concurrently develop the model and the software for the E3SM model, and with the testing and verification phase, with a number of simulations, which will involve analysis and validation, and then go on into the next iteration of the model development and the set of experiments. But the entire project is conceived and organized and executed with the idea of being able to maximize the productivity of the scientists as well as the scientific outcomes. And the advisory committee suggested, and that we were very highly ambitious in having to, in aiming to have the first version of the model released in a 4-year time frame, because it was practically unreasonable to think about that. But anyway, with the excellent management structure of the E3SM and the contribution of the scientists and everybody involved, and we were successful in releasing the model to the community at the end of April, as well as complete the deck experiments, one of the first modeling groups to be able to complete those set of experiments. So as we know, the Earth system model is essentially an aggregation of different Earth system components, namely the atmosphere, ocean, ice, and land components primarily. And then also there are, and our group, the project is organized around these themes, and also with the themes of major themes of the software, development of the model and being able to take advantage of the leadership scale facilities, performance, the computational performance of the system is also a very essential and critical element. So there is a performance group who focus on how to optimize the model for the different heterogeneous hardware. The coupled simulation group basically deals with the experiment aspects of it, getting the model tuned and ready to perform the coupled model simulations. And it's managed by an executive committee and also a council of all these task leaders or these team leaders, which make up the council. So I have been part of this workflow team in the first phase of the E3SM project, and I'm going to be talking about what we've been able to accomplish and deliver in support of the project as well as the model. So one of the challenges that we face is that it's a collaborative effort from personnel from many different Department of Energy laboratories and universities. So here I show in this map the various laboratories systems involved in the Department of Energy. As you can see, they are geographically distributed. And so that is a challenge in being able to work together. So the workflow infrastructure that we provide should be able to help all these scientists and developers work together effectively and communicate with one another. And the second part of it is that our computing systems are also diverse and heterogeneous, and they're also spread across geographically. So, for example, in the one in the lower right-hand corner is what I'm personally located in, the Oak Ridge National Laboratory. Currently, we have two major computing systems. One is the Summit system, which is currently going through acceptance testing and will be going and shortly followed by the early science phase of the project. And the other one, which is currently used for all the production simulations, is the Titan supercomputer. So Titan was, at the start of the project, was among the lead in the top 500, and it's still in the top 10, and still very much valuable for production simulations, including climate. Another one at the top is the Mera supercomputer with totally different architecture, which is currently at the Argonne National Laboratory. And a number of our model development and simulation activities also leverage that facility. And a majority of version 1 simulations were conducted at the NERSC supercomputer facility, particularly using the Cori and Edison supercomputers. And a lot of the DEX simulations were done there. And also we have some, at the Argonne National Laboratory, we also have a dedicated smaller scale computer cluster for model development and some limited production capabilities. So the fact that all our personnel are among distributed locations, laboratories, and also the computing facilities are also distributed, pose a great challenge on being able to collaborate effectively. So the charge for my group was to develop and implement a framework that would help accelerate the model development and the testing cycle so that the scientists can be productive. So that's one of the first challenges. And then at the end of phase 1, as the version 1 of the model is released, that we were also tasked and challenged with being able to successfully deliver the infrastructure so that using which the scientists should be able to seamlessly configure and execute the model across these facilities, gather the output and archive them or distribute them across the different computing centers, be able to generate the model diagnostics and the results, and be able to understand and synthesize them, and also be able to share the results not only in terms of the post-process result, but also the model data. So we were given the task of being able to deliver at the end of phase 1, which we have successfully done. So why do we need these kind of advanced workflow and data management techniques to support this modeling project. And again, as I had mentioned earlier, it's everything in the project is driven by the science needs. And one of the major science need is that especially during the development process, the model has to be configured in multiple ways, because the various team leaders are developing particular algorithms of the model, and they want to be able to run their own configurations on a test mode. And actually there were hundreds of these experiments were performed across various computer systems. And the results, they need to be able to quickly look at the diagnostics of the results, how the model is performing, and make any changes to the adjustment to the algorithms. Another major phase of the model development is being able to tune the model, and which again involve hundreds of these experiments, be able to quickly look at the results and be able to tune it. So with an infrastructure, we were able to do it. And that's one of the main reasons why we were able to make such rapid progress in being able to develop and test and release the model to the community. So there are many experiment runs, and then there are also, at this phase we did not do, but we are capable of doing, is that we can perform ensembles, large ensembles of runs for uncertainty quantification of the model. And on top of that, another important, when we perform hundreds of these experiments, that we need to be able to capture the history of these experiments and the model configurations, as well as the results, and maintain a provenance of all these activities, so that eventually we can go and look at the model provenance in case there are any questions, or even to get further understanding about either the model performance, the tuning parameters, or so many other aspects, and including reproducibility of any particular experiment. And then we also had to be able to do all these activities, be able to do them seamlessly. So the software, as we had mentioned, needed to be deployed on multiple hardware systems, and each user facility has its own policies, their own file systems with particular requirements, and we have to be able to handle that without the science team having to worry individually about how all these things are going to be handled for every unique site, or deal with the unique requirements of the various sites. And then also be able to do perform this evaluation of the model, oftentimes comparing against its own experiments, as well as observational data from satellite and in situ measurements. And we had to develop a new, actually redo many of the diagnostics package, and as well as the visualization software. And we are also currently working on being able to support what I term as in situ analytics in version 2 and beyond. The reason is that as with this increasing powerful hardware performance, then we should be able to simulate our experiments at ever higher resolutions. But there is also a challenge there, because as we go into even more high resolutions, it becomes impractical in many ways be able to analyze the results at higher temporal and spatial frequencies in a timely manner. So that means that many of these model diagnostics and evaluation activities needed to be done even post-processing, even as the model is executing. So we are developing our infrastructure to be able to support that in version 2. So that was not a major challenge during version 1, but we already encountered that problem, especially when we had to enable satellite simulators within the model, so that we can just compare the model results directly against satellite observations. So that had to be done on a limited basis, because that was not only computationally expensive, but also data intensive. So with the in situ analytics framework, we should be able to do that while the model is executing within the same facility itself. So the solutions that we came up with, I'm not going to develop. This is all the fine details of the various, how various elements of the process involved while performing the modeling experiments, what components of the various workflow components communicate with it. But I'm going to give you a simplified view. Basically, we can abstract that out and said, we start with a set of inputs, which is basically based on the science requirements. And based on the input, and the model is developed and configured for that particular experiment, and it's executed across whatever the computational center. And after the execution, the results are evaluated, and then a decision is made. And based on that, we go around the circle and we have a new set of inputs. So it's a spiral-like activity, and essentially these are the kind of what I refer to as a process flow that we need to be able to support that. And slightly more elaborate, if you look in the right-hand side, we have this workflow components and the input parameters that are needed for the modeling experiments, and the model execution, which is shown very highly abstracted, and then the post-processing activities that are done, and the output need to be archived, and decisions and the results need to be synthesized. The decisions in this case can be publications or synthesis of the results. So and all these things can be done seamlessly now by our software infrastructure. So next I will give you a quick overview of a service-oriented view of the system architecture that we are able to develop. So there is a user interface as well as a command line interface for invoking any of these services. The analytic services basically execute the analysis or the diagnostics, as well as some of the data integration, data migration, data movement, all that is taken care of. And the data services include the publishing of the data to the Earth System Grid Federation node that we have dedicated for the project, and also be able to capture the provenance in our provenance framework. The simulation services involve being able to execute the simulations across the different facilities. The data transfer, we highly leverage the Globus services, for which is supported by all the major computing facilities. And then we also take advantage of many other platforms for databases and message queues, and in the future, even software-defined networks. And we are able to do that because we were early on, we made a decision to adopt as many of the open source tools and frameworks that are available. And the Earth System Grid Federation that I mentioned earlier is used for the data management activities. The climate data and analysis toolkit is used for the visualization, and we have optimized it and implemented parallel versions of it so that the analysis, which used to take hours, now can be done in the order of minutes, and oftentimes within 2 or 3 minutes, even in the high resolution configuration. We have supported further extension and development of the NetCDF operators tool, similar to the climate data operators, and made it a parallel version of the tool, and also with the true Python bindings, so that can easily be integrated into many of the Python packages. We also use Matplotlib, and also have come up with a framework for to integrate the various diagnostics packages which are used in the community. In E3SM, there is also something called the ON diagnostics package. That's also a Department of Energy project involving observational facilities, and the PCMDI diagnostics packages oftentimes we used in the CMIP 5.6 analysis. And we also developed a new diagnostics package to evaluate the coupled model, which is called the A-prime diagnostics. We also use the CMOR software to be able to make the files CF standards compliant, so that it can be exchanged with the CMIP community. And there's a lot of others. I mentioned Globus is for data transfer, high-speed data transfer. We can do hundreds of megabytes sustained across the facility. So the data transfer is from a matter of days to a matter of minutes now in being able to share and exchange the data. And here's a very high-level overview of which portion of in the what we call the Acme Workbench, which forms the basis of the user interface, which software is used for that. And so I don't want to spend a lot of time on that, but basically this is another view of the framework that we have, so that everything works seamlessly. So all the components of the workflow is integrated via this Acme or E3SM Workbench. The project used to be known as Acme, but it was renamed to E3SM Energy Exascale Earth System Modeling Project now. So Acme is the former name for it. So the idea behind that is that so that the user should be able to submit what I call one job. Basically, all workflow tasks should branch off that single job, and the user needs to manage and monitor only that one job to accomplish the workflow process involved, instead of having to be able to integrate and manage easily 10 or more processes. And there has to be a single configuration to be able to set up and run everything and move the data. And all the low-level details are hidden from the user. And in case the job fails, then we should be able to go back and restart everything and start from rerun only those components of the workflow that needed to be done. And moving on real quickly, some of the functionalities we already talked about it. The important elements of work that needed to be done in data movement is accomplished via Globus across many facilities. We have improved diagnostics by developing and optimizing and parallelizing our diagnostic and visualization packages. We have also integrated a couple of other exploratory data analysis tools. And the user interface will be integrated via a common dashboard in the future version in phase 2 of the project. And I had already mentioned how the diagnostics and the NetCDF operator tools have been made faster and more efficient. And very importantly, that we have this provenance infrastructure to be able to capture all the stages of the workflow. And I'll skip that slide. And here's an example of some of the diagnostics plots that have been produced by our new E3SM diagnostics package. And actually a typical model evaluation, there are about 900 plots can be generated, and they are user selectable. And after these plots are generated, and they are what we call hosted in a web server unique to that experiment or that analytics part of it, and the scientists can go and look at the results of it at their own convenience. And I'll skip that too, and I will come to the provenance part of it, because this is really an important part with so many different pieces, and they are heterogeneous and distributed, that there is a harvester which harvests the provenance information based on model configuration files, including compiler flags, and the options used for generating the diagnostics. And everything is captured and stored in what we call a semantic store. And that from this provenance store, it can be visualized via a dashboard, a provenance dashboard, and we also have Jupyter notebooks to be able to analyze this data. For example, it happens not too infrequently that the model throughput performance sometimes degrades over time, even in the same facilities, for difference that are outside the control of the model, because there is probably some changes within the computing facility operating system itself, and oftentimes that may not have been because some of these experiments run for days, if not months, and with these changes, they tend to impact the throughput performance of the model. By going through this provenance information of the performance, then we can oftentimes monitor if if there is a degrading of the throughput, and then work with the facilities to understand what changes might have happened and why there is this performance is impacted. And at least one instance in the past that I was involved in, there's the MPI libraries. There was a small change by the vendor, which impacted which probably benefited many other applications, but it ended up impacting the Earth system model performance, and we are able to come up with a workaround so that we can sustain the throughput that are needed for the experiments. So in summary, our requirements for this project are driven by the stakeholders, which is the scientists and the developers, as well as the sponsors. And they are geographically dispersed across various DOE laboratories. And our resources are also distributed, and they are also heterogeneous. We needed to be able to automate many of the workflow solutions, which otherwise would have been much more laborious if they were to be done manually. And then we are able to share model configurations and the results and the data across our collaborators within the project, and sometimes even outside the projects in universities. And we have demonstrated that the model development cycle could be accelerated, and we could deliver a finished product in a much shorter time scale than it had been possible historically. And through the Provenance, we are able to now reproduce not only our analytics, but even some of the model simulations, provided other things haven't changed, external things haven't changed in the computing facilities. And the framework that we have is flexible, and it can be extensible and probably adopted even for other Earth system modeling projects. So we have laid the foundation for further improvements and efficiency in version 2 and beyond, going toward our 10-year roadmap to be able to meet the requirements and challenges of the Earth system modeling in the Exascale era. I also want to acknowledge the sponsors, the Department of Energy Office of Science and the Biological Environment Research Office from the U.S. Department of Energy, who funded the project itself. And I personally also was supported by the Oak Ridge Leadership Computing Facility, which also supports a large portion of the simulation activities in E3SM. So Sandro, I'll turn it over to you for questions.
Thank you, Valentine. Great presentation. You touched several aspects. I'm sure this will stimulate a lot of the discussions. But before going to the discussion, and I will ask all the registrants to submit some questions, and then I will pick up some of them in a few minutes. I just want to comment a little bit on your presentation, which was really comprehensive with a mix of computational and data aspects. That I think there could be tens of questions today for based on this material. So I really liked some of the aspects in your presentation, like for instance the integration between the strong and huge backend aspects that has to do data crunching, data processing, and analytics, and then what the end user sees somehow. So very lightweight front end that could be Python based, like Jupyter and so on. That's really a way to bring science to the desktop of the scientist, and while dealing with the very large and challenging amount of data. You touched also other aspects that are becoming more and more key, like for instance the provenance and the reproducibility of the experiments, and you are really addressing these aspects in your projects, as well as also I think some foundation level services like the data transfer one, and that you're managing with the Globus or Grid FTP that it's widely used also in Europe. So based on that, I just want to open the question time with a question. So that's a project that is looking forward the Exascale era. So how do you see this project contributing to the Exascale roadmap? So what are the aspects of the Exascale you think this project will be able to address or to tackle?
Okay, so that's an excellent question. So first of all, as we look into the exascale, and we had asked, is that what is the science that we should be able to perform, assuming that we'll have access to exascale resources. So in fact, that is an ongoing project, which is not technically under the E3SM project or its roadmap, but it is a parallel effort under the US Exascale computing program. So as part of that project, and in fact, the activity is, that's going to be one of the early science activities even on Summit in 100+ petaflops, is to be able to enable cloud resolving model, 1 kilometer cloud resolving models. In this case, 2D models within every grid cell, a E3SM grid cell. So it is based on this super parameterization approach that's used by, in this case, in E3SM, we are working with the scientists at the Colorado State University. So that will be one of the early science and applications on the Summit platform, which will be conducted actually anytime when the machine passes acceptance. So that is the roadmap, and being able to perform this cloud resolving simulations with the target of 1 kilometer is on our exascale roadmap. And after whatever is developed under the ECP will be brought into version 3 and beyond of E3SM, so that it can become part of the E3SM mainstream package.
Okay, so one more question is about, so you mentioned in your presentation server-side analytics and processing as part of the version 2 of your release plan. So can you elaborate a little bit more on what's the concrete plan, or what do you think that will be put in place for the project?
Okay, I understand your question there. So the server-side analytics is going to be, because we are leveraging the ESGF framework for our data management, and the server-side analytics is a major component of the ESGF development activities. So we expect to be able to leverage that activity in working with the ESGF team. And in fact, one of the developers from our project is also half-time involved very actively with the server-side compute work team of the ESGF project. But then there are also other exploratory projects. For example, that we have this facility, smaller facility called CATES at Oak Ridge, where we have a node where Ophidia is deployed. We're also looking at Python Dask frameworks and maybe even array-based databases so that some of this analytics can be performed. And the in-situ analytics that I refer to is that it's going to be based on the ADIOS framework that is developed by Oak Ridge, but now currently it's part of the US Exascale project. So it's one of the mainstream projects. And already many other simulations are using that very effectively to do their in-situ analytics while the simulation is running.
Okay, thanks so much. So we got a question from Franklin, PhD student from University of Massachusetts, who is asking, is it going to be possible to integrate E3SM with integrated assessment models like a GCM?
That's a very good question. In phase 2, there is already a component of that. There's a group, there's a DOE laboratory which is leading an effort to be able to integrate that into the integrated assessment models. And when phase 2, version 2 of the source is released, and that'll be part of the official release of the software. But meanwhile, if somebody is interested, I will always be glad to put in touch with the personnel who are involved in working on that.
Okay, we have a question from Giovanni Aloisio from CMCC, and the question is, can European research groups contribute to this project? Are collaboration with external groups possible?
The audio was breaking up a little bit, Sandro. So are you asking about collaboration with external groups? Is it possible?
Yeah.
Yes, yes, it is possible in various levels. So oftentimes, policy, there is a formal policy on how somebody can collaborate. So there has to be a collaboration agreement, which is not exhaustive, but which can be formalized so that even experimental versions of the code can be shared.
Mm-hmm.
And one thing which is possible not through the project but externally, if somebody needs computing resources, the leadership computing facilities welcome proposals from anybody in the world. It's not limited only to DOE or only United States institutions. In fact, we have several groups in different areas of science collaborating with Oak Ridge and other leadership computing facilities. So that's on the computational side.
Okay, so thank you so much, Valentine. So I think we have reached the end of this webinar today. So we got several questions that unfortunately will not be able to deal with today, but these questions will be forwarded to Valentine for any possible follow-up. So let me remind you that this webinar has been recorded and the link to the video will be shared with all the registrants, as well as will be disseminated and uploaded on the CMCC website. Our next CMCC webinar will be in September. The topic will be announced on the CMCC communication channels very soon. So before leaving, let me thank again all the people that attended joined the webinar today. And I would like to thank in particular our speaker, Valentine Anantaraji. Thank you very much. We really much appreciated this contribution. And this webinar, I think, was a great success today. We got a lot of people, more than 100 joining the webinar today. So I think it's been really a great webinar. So one more thanks to all. Stay tuned with our next events and have a nice rest of the day. Bye-bye. See you.
Bye. Thank you.